I calculate.
You have multi-center, not just.
All right. Excuse me, everyone. So sorry for the delay. So today we are very happy to have Keshav from McGill University, and he will tell us about what it is to have a digital.
Thank you very much for the invitation. It has been really nice, and thanks for all the arrangement and everything. Especially and Catherine for inviting me here. So my talk today will be what if string theory has a de Sitter excited state. The title has there is a reason for choosing this title, and that's because, of course, it's based upon papers over here. And as you know, that the work on de Sitter has been become very intense for the last few years, with half the people saying yes, other half saying no, and the remaining doing CFT. So it's based on these papers that I wrote some time back, and as I said, it's based mostly to answer the question raised in this first paper over here in 2018, that what if string theory has no de Sitter vacuum? After going through a few years of work, we realized that the statement may be correct. De Sitter may not actually, string theory may not actually have a de Sitter as a vacuum solution. So we proposed that maybe in string theory, de Sitter exists as some kind of excited state in the theory. So that's what I'm going to present. And there is some other work which I did with other people here. So the summary is the following, that I will discuss the problem of realizing de Sitter as a vacuum solution, and then how to realize it as an excited state, which we call the Glauber-Sugerson state, instead of a vacuum. Why is this a hard problem? What I wanted to say, and even if it is a hard problem, maybe it's still a doable problem. So let's start with this. Imagine somebody in 4 dimension gave us this kind of action, an action of this particular kind. So which one should I press for light?
This one.
Okay. If somebody gives us a 4-dimensional action with this kind of stuff over here, with a cosmological constant over here, then there is nothing to say. Actually, we can just finish the talk right here, because this cosmological constant, if it is positive definite, there is absolutely nothing new to say over here. The problem is exactly this particular action in 4 dimension. String theory, turns out, does not come with this little factor. This little factor, you see, is actually it's not there in string theory, directly there in string theory. So in other words, we can ask the question that in string theory, say in 11 dimension, we have an action of this particular form. If it dimensionally reduced to 4 dimensions, say for example in 4 dimension, then can we get that little factor out there? The answer turns out to be yes if this lambda is negative or 0, and no if the lambda is positive. That's the little thing in string theory that make us look into it. It may look like a bold claim. For example, we are actually claiming something that if this is the Minkowski over here, and if we want to study a vacuum of this particular form, as it exists in string theory. As I will show you that maybe such a kind of potential for any moduli or anything does not probably exist. So what's going on here?
Is this requires internal space has to be compact? Like that is
If the internal space is not compact, then the Newton constant will become 0. We want a non-zero Newton constant, so internal space has to be compact for most cases, or at least normalizable in some sense, to have that finite Newton constant. Okay, so the claim now we are making is that
non-compact with finite volume. There are non-compact spaces with
finite volume. Yes.
Will they still have this property?
Yes. Yeah. As long as it has a finite volume, internal space as a finite volume.
If it is non-compact, you'll have this
Even
property.
if it is, no, I will come back to that. Thank you for raising this question. I'll probably discuss that thing. It has to do more beyond some other aspect.
And if I give up supersymmetry, still,
Huh?
if I give up supersymmetry,
That also is an important thing. Maybe I'll come back to the issue of supersymmetry. So the claim we'll be making is that, so here is the claim we are making, that maybe the potential in string theory is always of this, the Minkowski thing. And we are taking supersymmetric Minkowski over here. So all the minima are Minkowski with possible ADS minima, although scale separated ADS minima also does not appear. So that's the claim we are making, and it somehow seems to be ringing, at least true for us. Anyway, let's see why this is the case. To study this, we'll use M theory. So you might immediately ask, we know nothing about M theory. The answer is yes, we don't know anything about M theory. But we know something about M theory. We know the low energy dynamics of this theory. We know what are the degrees of freedom over here. But one other thing we know about string theory or M theory, even though we have no idea what is the ultraviolet degree of freedom, M theory, or what degrees of freedom resides at the far ultraviolet or a short distance, or even there is a Lagrangian description of M theory or not. But we know for sure that the short distance behavior of these theories are good. That is on which we rely all our thing, even though we have no idea what
I understand this statement for M theory, but I'm a bit surprised that you make it for string, because string theory is always the selling point is that is UV behavior is wonderful, we know it, it's good, and so on and so forth. Why is it that you say you know nothing about UV behavior of string theory? I'm surprised.
We don't know what degrees of freedoms are there in the far ultraviolet. We know that
Non-perturbative, probably, degrees of freedom.
there might exist, but we
Perturbatively,
have no
what is
idea. For example,
perturbatively
we
is
know-
just Reggie trajectories. What else is there?
Yeah, we know, for example, D branes, RAP D branes, or other kind of non-trivial objects will be there.
I see. That's
Yeah,
what.
not just the perturbative. Okay, I'm going beyond that.
Okay.
Yeah, so that is the point over here. So now what happens is, so this is the scale we see. Imagine there is some theory right at this particular scale whose degrees of freedom we don't know at the both at the perturbative, non-perturbative maybe we know, but non-perturbative we don't know. But here all degrees of freedom over here. But we know that whatever resides over here is at least well-defined. The theory gives a well-defined theory. And if we directly follow the exact renormalization group, we can study the theory in this particular scale over here. And in this case, one can study that we'll get an infinite towers of irrelevant and marginally relevant and relevant operators over here. And the coefficient of these operators will contain all the information of the far ultraviolet in your theory. With this assumption, we'll proceed. In other words, we have to keep track of all possible operators constructed from this theory, which is, of course, a very hard problem already by itself. And the more hard problem would be that some of these states are, of course, can become optional and all these things. So there's a lot of issue there. So question is, under all of these conditions, can we see something positive in this setup? In other words, let's first ask the question. Let's ask the question like, what goes wrong with the solution like this? For example, if we make an ansatz in say type 2B theory, for example, we say that our space-time is a four-dimensional de Sitter, and here is an internal space over here. So with this kind of assumption, we can plug it in the equation of motion and all these things. So what goes wrong, and why are we saying that there is no vacuum? So we'll take this kind of ansatz. Okay, and we'll, for a mathematical simplicity, we'll just lift it to M theory, because that's where the analysis is simpler. So we take an ansatz of this particular kind in type 2B theory, and we lift it to M theory just for mathematical simplicity. And then we put in all the fluxes and all these things, try to solve the Einstein's equation. And when we add up this Einstein's equation, we get a solution, get a consistency condition. Now here is the point. So here is the fluxes which can support such a solution. Here is the brane, anti-brane and all this thing. Here is all the information of the orientifold plane and all this thing. Now you see, if I have no quantum correction in my theory, then this is positive definite, this is positive definite, this is positive definite, and this sums to 0. So there is, you see, there is no solution in this system. So in the absence of any quantum correction, if lambda is positive, then there is no solution to the system. The solution is identically 0, which is of course the Maldacen and Nunez no-go condition, Gibbons Maldacen and Nunez no-go condition. But you see, even in the absence of quantum, if lambda is negative definite, then you see there is a solution. So ADS spaces are quite easy to get in theory and all. But to get a positive cosmological constant in the absence of quantum term, it's impossible to get, first of all. So you might say, okay, why don't I throw in a quantum term? And you see that as long as the quantum sum of all the quantum pieces is negative definite quantity, then we might be able to have a solution in this system. So there might be a way to find a solution in this system. So what's going wrong with this simple idea? Okay, so that's the point here, that with all the sum of all the quantum pieces to be negative definite should have a solution. So this looks like some kind of a good news. The good news is that if we allow some kind of hierarchy in all this quantum term and satisfy the condition that I just proposed, we might just get a de Sitter vacuum solution.
What do you mean by hierarchies?
Yes. For example, when I say that I have to put the quantum pieces over here, you see that I'm somehow balancing the classical with the quantum terms. That is already suspicious because there is no way you can balance. So that means now the quantum pieces can be classified with respect to powers of G string, for example. Okay, so then we need to see to what order in the G string should I go to balance this equation over here.
So by hierarchy, you mean orders?
Order by order in G string.
Order in G string.
G string, say for example.
You're suspecting that you may need to sum to
Yes.
balance the other one.
That's right.
I see. Okay.
So that's what I meant over here. So, so this looks like something of a good news. I mean, maybe we might be able to solve that above equation and might get a solution, vacuum solution. What goes wrong with this simple idea? Now remember, there is something I haven't clearly mentioned to you, that we are studying everything at the far infrared. So this quantum term, which I talked about, must have come from integrating out the high energy modes or heavy degrees of freedom in my theory. Must have come from doing this. Now comes the question, what if we could not integrate out this high energy degrees of freedom? What if that in that previous thing, we have, for example, we are taking a situation in which I have a, say for example, de Sitter minimum over here, and I'm studying small fluctuation over here, and I'm integrating out all the high energy degrees of freedom over here. So question is, what if I cannot integrate out the high energy degrees of freedom?
Why could you not? What could possibly prevent you?
That's right. So question is, what could possibly prevent me? Now there's two ways it can prevent. One is that maybe there is no well-defined UV completion. We can rule out the former. Of course, we have claimed that. But there can be another probability, which is that maybe the frequencies are themselves changing with respect to time. The fluctuation over here on top of the fluctuation. See, what did Wilson say? Wilson says that take a high energy mode over here. For example, there is a high energy mode over here, and there is a low energy mode over here. So we can integrate out this high energy mode to write an effective theory in terms of low energy mode. That's how the Wilsonian prescription works. But this works precisely because the high energy frequency over here are static. They don't change with respect to time. What if the frequency themselves are changing with respect to time? For example, the frequencies are, you take a high energy mode and slowly they are redshifted to become low energy. So then this whole integrating out procedure would not make sense. Yes.
So you consider compactification on space-like manifold. What if you consider somehow like a
Static patch.
No, I mean star to be a something like that, and on time-like manifold instead of space-like manifold. And you have a negative sign, and you don't have this no-go theorem.
Yes. So first, let me explain the problem with this thing, and then maybe you ask me a little bit later the same question. You can ask me a little bit later. So if the frequencies are themselves changing with respect to time, we might be having a problem, of course. So that is an issue. One of the biggest issue is that on a background like that, over a de Sitter, the frequencies are actually redshifted constantly. And this redshifting actually tells us that the Wilsonian integrating out procedure has no meaning in this kind of setup, because as soon as you try to integrate out a very high energy mode, it immediately becomes weak energy, low energy, and so on and so forth. So this whole integrating out procedure does not make sense in a Wilsonian setup, in a Wilsonian way. Of course, this was known for some time now, which led to many kind of problems in the study of de Sitter in quantum gravity and all this thing. So then how did people deal with this one? The way people dealt with that, they went to the static patch. The question is that what if I go and take everything to the static patch? For example, here, I plotted for you a high energy mode over here, and in the Wilsonian sense, I'll integrate out, and you see with respect to time, these modes are not changing, so I can integrate out these modes over here. These are the high energy mode in a static patch, and that's what people have been doing by integrating out this high energy mode in a static patch. What goes wrong with that? The answer is that static patch is a very small patch, but from a global point of view, this is how it looks like. So these are the persons sitting on the static patch will see that the modes are not changing with respect to time. But if you use the coordinate of the global patch, you can see that this mode is completely different from that mode, and these modes are completely different. So you'll be making a grave mistake by integrating out these modes, because these modes are actually in a static patch and not changing with respect to time, but they are actually changing with respect to time from a global point of view. But the observer in a static patch will not know about it. And this has been static patch, as is known, is a very deceptive system. Of course, it was known for some time now. And that's the thing. And for example, a different observer with slightly different static patch will notice this, of course. If I go back and I have another static patch which is slightly along that direction, that observer will, on his static patch, his modes will not change, but he will see a changing mode in your static patch, because in de Sitter, every observer has his own static patch, unlike black hole, where the static patch is more or less.
Can you remind us in the nutshell the definition of the patch, the static patch you're talking about?
Yeah.
What's the definition of it?
A static patch is where the metric is written so that it has no time dependence, no apparent time dependence.
No apparent time dependence. It's a coordinate transformation?
It's a coordinate transformation. Yes. Okay. Coordinate transformation. Okay.
I'm a little confused.
Yeah.
So this integrating out procedure, are we not sort of assuming that this is happening behind the curtains and we don't have to worry about it? So you say
not
like that.
Not in an accelerating background.
Okay.
That's what led to this idea by Robert Brandenburger and write a paper called Transplanckian censorship and all these things. They knew that they saw that the modes are changing with respect to time, which means that if you start with a mode, so their paper was that since we know Einstein gravity has thickness at short distances, but the short distance mode will become long distance at late time. So this long distance mode will bring all the sicknesses in our low energy. So they wanted to put a censorship on that. So many years ago, they wrote a paper showing that this mode, which they call it Transplanckian, should not enter our Hubble horizon. So that's how they, but inflation does bring those modes to our Hubble horizon. So then they claim that inflation cannot be the right way to deal with this system. So these modes cannot enter. So there was a long history of this one. Not that something I'm saying which is new, but it has not been appreciated more. And more, in fact, surprisingly, a few months later, Banks had exactly the similar observation, Tom Banks. He found that even in a static patch, the energy is leaking, which is what would happen, I believe. And there are other issues. So you see, this whole integrating out procedure on which we base our holy grail of physics
does not cover all of the Sitter space.
Does not cover all of this.
Partially
covered. So the global patch covers. In global patch, you can see that integrating out procedure doesn't make
sense. How many of them do you need to cover? Is there
a certain
who will be sufficient?
Yeah, so if I draw the Penrose diagram, that's the static patch, and yeah.
So you can do it globally with 2 static patches, you're saying?
Yes, so you can do it, but you have to insert those kind of other things here, so.
Is your static patch terminated by horizons at both at each end?
From one point of view, it has a horizon, on the other, yes. Yes.
So when you say that the modes are time dependent, so we can't do the usual integrating out thing, does that mean that there's no link between the high and the low energy?
That's right,
theory
because there's redshifting of modes.
But then how do we relate the UV complete theory?
So that's why you cannot in such a background.
So yeah, so are we saying that the low energy theory which we're looking at is true, or are we saying that it doesn't?
Not on a de Sitter, there'll be some UV IR mixing and all this thing will happen.
Okay,
It
so
becomes very messy, so that's why to avoid such modes to enter our Hubble horizon, there was this Transplanckian bound was proposed by Brandenberger and his collaborator on that.
so would it lead to things in the low energy theory that we wouldn't usually
See,
okay?
yeah.
Yeah.
For example, if I take Einstein gravity, we know that the short distance behavior has a problem. That means the mode, very short distance mode, which has the thickness of the Einstein theory, will become redshifted and will enter our low energy domain, carrying all the bad things about the UV.
Okay.
So creating problem in our low energy theory, which led to their famous prediction that this mode has to be completely censored. So that means there should be a time limit beyond which, because this takes some time to become bigger, beyond some time, it should somehow, there should be a censorship. So that means if there's any inflation, it has to stop at certain time, which does not really happen. So they ruled out inflation as a viable technique to, there's a long story about that thing over here. It's not very well appreciated because we always bring down to static patch and we study where we see no apparent problem.
Okay.
That is the thing. Is that good?
Yeah, that's helpful.
Yes.
Thank you.
You can find more details in those papers, earlier papers. Long argument with group of Brandenberger and Andre Linde and other people. Their fight has been going on for ages now. Now, how do we do it then? Of course, we see some problem. There are 3 ways we can ignore it. We can ignore it or use open quantum field theory. There are some branch of people now started using open quantum field theory where energy is not conserved. I don't think I'll have the thing. Or third is the proposed the Transplanckian censorship. So this is the thing has been taken. There is a group of people who use something called open quantum field theory. Now, open quantum field theory, as you probably know, again, I'll not have much time to say, it's a theory in which you study using only the relevant degrees of freedom by making some part of the theory to be an environment, but it's very difficult to realize in string theory. So open quantum field theory, typically these things now has been appreciated by Cliff Burgess and other people. So they have started working on open quantum field theory way of dealing with all these things. But this cannot be embedded in string theory, so that also rules out this. Now, what about cosmic censorship procedure? But remember, original cosmic censorship procedure that was proposed by Brandenberger and company, they relied on the fact that they wanted to take this UV mode to not go in the infrared because the far ultraviolet behavior of Einstein gravity had some thickness. So this mode will carry those signals. But we know that the far ultraviolet behavior of string theory is well defined. So that cannot quite be an argument to actually say that we can avoid this. So all of these arguments using either censorship and all these things doesn't exactly make sense. So all these 3 arguments are unsatisfactory. So that's where we realize that de Sitter as an excited state over supersymmetric Minkowski background might actually take care of all the issues that we have studied over here. So how does that do? Is that now we claim that there is no potential like that. By the way, this is also the conclusion of Wafa and all, that there is no vacuum solution at all. They arrived at it from a different angle. We arrived at it from a different angle. I'm not quite sure what they are saying though, but The claim now we are making is that there is always a potential supersymmetric Minkowski in this theory with some ADS minima somewhere here. But those are not, they are non-scale separated ADS minima.
Is there a theorem that will say that there will always be no scale separation?
No, there is no theorem.
So if
Yes,
somebody
maybe, yes.
finds a model where there's
So
a
far-
separation, that might change the problem then.
They might change a problem.
But as we speak, you are not aware of such.
Well, the claim of BAFA is that scale separated ADS are in the swampland. The claim they have written.
So he claims.
So he claims, as you said.
Okay. So far, that's the party line at the moment. Okay. Thanks.
Right. So now, how do we create? Well, the way we created is that the following. So this we'll call a Glauber-Sudarshan state. We take some interacting vacuum and we shift it by some displacement operator, much like the way you create a coherent state. We call this kind of state as a. So if I draw it like that, for example, if I take a vacuum, say, let me just draw this vacuum to be like that. This is the harmonic oscillator minimum vacuum over here. This is the ground state of the harmonic oscillator. I'm drawing it in this direction and will oscillate. So these Glauber-Sudarshan state are the state in which you shift this vacuum by some like that. You shift it like that and you leave it. So it will oscillate up and down like that. So now that the problem with such a simple construction this is a coherent state construction, of course. So the problem with the coherent state is that coherent state relies heavily on the existence of a free vacuum, but we know in this kind of theory there are no free vacuums. So what we did is that we took some interacting vacuum in the theory and we shifted it by some kind of displacement operator. How do we calculate anything out of that? For example, I want to calculate the metric out of that kind of construction. So we take the metric operator sandwich between two coherent state and we calculate. So this is how we call that. That's how we compute the metric of, for example, of any of our system.
This parameter sigma, how should we think about it? Like it's a displacement in.
Yeah, so it's a displacement in the configuration space. In the language, like it's the Fourier component of some kind of metric configuration. It will turn out to be the Fourier component related to the Fourier component of the metric configuration. Okay, so that will act as a displacement. I'll show you a concrete calculation. Okay, so that's the way we claim that. So how does it work over a Minkowski background? For example, you can take the Minkowski background over here. And how do you define the interacting vacuum? Take a local Minkowski minima over here. And imagine the whole system has some low energy state, omega x, low energy minimum state, which we call it as. So imagine there is a Hamiltonian governing the system whose eigenstates are given by omega and n. So you write a local minima in terms of a linear combination of that. And you hit this guy left and right hand side by e raised to power minus this h total on that one. And take t going to infinity 1 minus I epsilon, then you can express this local minima in terms of these things in this particular way. So that means this interacting vacuum is nothing but your local minima by this operation over here in the limit t going to infinity. Similarly, the bra is along that direction, which means that using this kind of trick, you can take an expectation value of a metric, which I write it in this particular way as a path integral. This is how you convert a metric as a path integral over here. You see, this is all the metric, all the flux, all the thing over here. This is the e to the power minus s. This is the d dagger d. This is the metric operation divided by normalization factor over here. So all the calculation of the metric can actually be done from the path integral point of view in this particular. Any question?
Shouldn't you also have, like, if you calculate g square expectation value, it should be small compared to, I mean, that's only the expectation value of one of
metric.
You consider like square, cubic operators, etc.
Right. So if you consider square, as you said, if I consider say g square over sigma, for example, right?
Yes.
So I can write it as sigma g sigma, and then I have to put a resolution of identity over here. And we put the resolution of the identity. The first term is sigma g, sigma g, sigma plus all kind of thing. So this is nothing but expectation value of square plus additional stuff over.
But you want additional terms to be small, right? I mean,
Not
you want
necessarily, but they will be there. We are putting no constraint at this point, but as you said, I can write it. Yes, sorry.
I was going to say, aren't the coherent states usually over complete? So if you're
Yes, so
resolving
these are
them,
over complete state also.
so you have to also divide by some stuff, right? I mean,
Yeah, the division is already taken into account over here.
I see.
So every time I write, I have to also divide it by, so this correct thing is to divide it by sigma sigma. So this will turn out to be, so sigma sigma, you divide it by that, and you put the identity operator again there, so you'll find that this is sigma square and so on and so
Yeah,
on.
it's the resolution of the identity that I'm a bit worried about. So when you write the identity as a sum over the coherent states.
Yes, it doesn't come out that simple.
Yeah.
Because these are the not constructed as a coherent state. So it's not exactly a sum over all these things. There are new operators which appear. This is a little more complicated resolution of identity. So in our most recent paper, we derived the resolution of identity for it. Yes.
So what is the displacement operator, roughly speaking? Is it some like integral over a bunch of
Yes.
different states?
Yes. So the displacement operator here, say in the path integral language, it's e to the power of minus s. Maybe I use something dark. E to the power of minus s, d dagger, gd, for example, something like that. Okay, I have in the path integral. So e to the power of minus s is like e to the power of minus k square, phi k square for all k, right? For a scalar field theory, and d turns out to be e to the power of sigma k phi k. Okay, sum over all k. So this is the simplest one.
Okay, where
So
sigma.
now if I put, take the simplest one, if I put e raised power of 2 sigma k phi k, then you see what is happening is that I can complete the square over here, become e raised power of minus k square phi k minus sigma k square. You see that the minima has shifted. In this
Okay,
way.
okay, yeah.
So this is just a linear term over here. That's the simplest one. You can add other term over here, but this works. And this actually goes in, complete the square, it shifts the vacuum minima of the vacuum in this way. Now when you shift it, now you see these two goes up and shift the vacuum. So that means the 1 point function is no longer 0. Otherwise the 1 point function would have vanished, right? 1 point function in a path integral always vanishes. But because the vacuum is shifted vacuum, the 1 point function is non-zero. And in fact, 1 point function is exactly proportional to sigma k, and that determines the Fourier component.
Thank you.
Okay, the answers. Okay, then there are, of course, but once you write it as a path integral, you know it's very dangerous because you have to use ghost and all kind of stuff to make this, for this to make sense. We'll not have time to talk about this thing over here. And other
To be 11-dimensional supergravity.
It has to be, yeah, so S total should be 11-dimensional supergravity, but will not restrict it to supergravity. We'll add other terms in the theory, higher curvature corrections and all.
You need the higher curvature correction.
Yes, otherwise there is no solution in
Up
this.
to what order? You need that.
Good. In 2 slides.
Okay, thank you.
In 2 slides, we'll come back to this one. But also there will be ghost and all this stuff. So for this to make sense,
But ghost comes with, there's a prescription, right, for ghost. We don't need to invent anything new.
no.
Yeah, okay.
But something bad happens that which we did not know before, which we recently came to realize, is that this series, even if you add all kind of things, this series is actually asymptotic, not convergent. So perturbation theory, or if you write S total in terms of a perturbation theory, this theory is actually asymptotic. Because perturbative theory is asymptotic. So this actually explains, for example, if I have a I have a perturbation theory. Let's take lambda phi 4 theory if I take lambda phi 4 theory, e to the power of minus k square phi square plus lambda phi to the power of 4 theory over here. Then if I write it as a path integral, then it will be e raised to the power of minus k square phi k square over all k's. And then it will be 1 plus lambda phi to the power of 4 plus lambda square phi to the power of 4 lambda phi to the power of square and so on and so forth. So at the nth order, one can show that at the nth order, it will look like e raised to the power of minus k square phi k square. And then it will look like lambda n phi to the power of n divided by n factorial at the nth order. The problem with this thing is that this thing at the phi to the power of nth order, this grows as n factorial, and therefore this series is actually not convergent. So that's another problem, but this is good for us because if a series is not convergent, so that means we can actually Borel resum the whole thing. Once we Borel resum the whole thing over here, then we can see how the non-perturbative effect appears in this kind of setup. So now that explains, which means that if you have followed a little bit about the literature of the so-called resurgence, whenever we see an asymptotic series of this particular form, then the action S total is written as S1, the perturbative action at the 0 instanton sector, then S2 perturbative action with e to the power of minus first instanton, plus S3 perturbative e to the power of minus second instanton, and so on and so forth. So we have to rewrite this action in terms of the perturbative series, first instanton sector, and then so this perturbation series is the one which makes sense in the absence of 0 instanton. Then in the presence of 1 instanton, this is the fluctuation determinant. We determine the perturbation series and so on and so forth. So just because of the asymptotic nature, the action that actually enters in the theory cannot be a simple action of this form. This will be the action at the 0 instanton sector, which includes all the curvature, higher curvature terms and Einstein 11-dimensional action. Then you have to add back all the other stuff over here. So an action will look, a typical action will look like that. It will be the 0 instanton sector and then the fluctuation determinant. So this is called a trans-series form of the action.
I think I missed something. So the whole talk is based on this current state, but you haven't mentioned about what field that you consider. Or is this dilatant field that?
Yes. So the coherent state is for everything. So this is the coherent state for the metric, which I computed G mu nu. But it's also the coherent state associated with, so this sigma, which we call as a coherent state, is associated with the coherent state for the metric, all the metric component, coherent state for all the fluxes, coherent state for all the fermions, all the on-shell degrees of freedom. So they are coherent state associated with everything over here. So there is a metric coherent state, flux coherent state.
But this is not that simple. Like you have a curved space-time, then you need to solve it like 11-dimensional supergravity.
It's over a Minkowski. It's over a Minkowski, flat Minkowski background. So these coherent states are all constructed over a Minkowski background. And from there you generate the
plane wave.
Huh?
All of them are just plane wave.
All are using plane waves, yeah. Except that the action is more complicated, but it's constructed over a flat background. We claim that there is no more non-trivial background other than the Minkowski. The system always has a Minkowski minima of this particular form. And we are studying fluctuation here with the Minkowski minima. And of course, there is possible ADS stuff over here. And we are studying the theory over here, and we are creating a coherent state over here using this kind of, by shifting this operator. This coherent state, when we take the expectation value of the metric operator in this coherent state, then we get non-trivial background of this form. But everything is done over a Minkowski, supersymmetric Minkowski.
And instantons you are talking about just between the Minkowski work.
Yeah, these are all the real and the complex instantons. So there is, for example, if I have a As you know, in the literature of this, if I have a Minkowski minima like that, then of course there is a real turning point, which is the real instanton, but then there can be also be complex turning points, the so-called complex instantons. So both this instanton, all this, and then there are multiple over here, so there can be real, all the real turning points and all. Just turn the potential around, and then so you'll have this series of instanton, both real and complex. It'd be nice to just set up over here.
Where's the potential to determine this minima? I am confused. How do you get this profile?
The profile is a conjecture that the system only has this profile. This is the potential for, say, for any mode. For example, let's take any, say, radial mode or any mode of your theory. All the mode will have this potential like that. So there is only the Minkowski minima possible. We don't know the shape of that one, but the claim is that everybody will have a Minkowski minima as the potential. That's the claim. So by the way, there is another group led by Gyadiwali and company. Gyadiwali, and they exactly found similar. They also found exactly similar construction also.
Your philosophy is to work as much as possible in a model-independent way.
Model independent.
That's what you're trying.
Yes.
So this potential is really depending on your compactification process.
Yes, and the claim is that there is only Minkowski potential allowed. No, there is no other non-trivial potential allowed in this system.
And you said Wafa claiming even ADS doesn't.
Wafa is claiming even a scale separated has problems, but he's at least saying that there is no potential like with the positive energy. That part we agree. Gyadiwali and company in fact came to the same conclusion. They also have coherent state construction, but they are doing in a different way. They came to the similar conclusion that it's a way to deal with that system. So there is this whole story about this thing, and you probably know very well how D-brane was discovered. D-brane was actually discovered using this idea only somewhat, that what Shankar noticed many years ago, that if you take a string perturbation theory, it is asymptotic. And if you Borel-Rissam the string perturbation theory, then the correction goes as e to the power of -1 over G string. From there, he claimed that there should be an object whose strength goes as e to 1 -1 by G string. And then he predicted that there should be D-branes in the theory. That's long time history over there. So that means that also shows why there are non-perturbative effects in physics at all. Now at least I understand after talking with many people like Mita, Tunsal and all. I think now we know why nature has non-perturbative effect. The reason nature has non-perturbative effect is because perturbation theory is always asymptotic and it blows up. So to make sense of the perturbation theory, we have to Borel-Rissam it. In other words, perturbation theory should not make sense, as Dyson pointed out many years ago. Even in QED, perturbation theory should not make sense. And we observe that in QED also at like 400th loop, theory blows up. So there should not be any perturbative series at all. What would happen is that at best the theory can have trans-series in the form of that, the way I wrote over here. And these corrections are these non-perturbative waves which come from Borel-Rissaming the whole thing. If I have a chance, I will tell you how exactly those goes. Okay. So now what we are claiming is that to get a background, remember this was the problem we had. If you wanted to get this background as a vacuum solution, instead to get this background as a vacuum solution, I lift it to M theory just for simplicity. If I want to get this particular background in my theory, I'll not get it as a vacuum solution. For example, the first term, which is G00 or G mu nu, goes as 1 by lambda h squared t squared. So this I should not get as a vacuum solution. Instead, I should get in the following way. I should be able to take an expectation value over this and I should get an answer of this particular form. So all the components of this metric which you see over here should not appear as a vacuum solution. Instead, they should appear as some kind of expectation value. So we call them emergent state. So that means the whole de Sitter may actually not be a vacuum state, but something which emerges out of a coherent state. And one can show that the cross term vanishes and so on and so forth. Something other very interesting also happens. We found that if we demand that the non-perturbative effect, which is e to the power of -1 by g string, to have a convergent series of this e to the power of -1 by g string, this thing goes as e to the power of -1 over g string, e to the power of -2 over g string. To get a convergent series, we need g string to be at least smaller than 1. That leads to this condition, which is that the time period for these state to exist should lie between that. This is the cosmological constant over here. So when we proposed this answer, Robert came back and said, this is exactly the proposal they had many years ago, that the Transplanckian bound is also exactly that, actually.
Can you quickly show me the previous slide? There's one thing. Okay, so on the left-hand side of your G mu nu or whatever you're
Yes.
taking the expectation value of, there's a state between which you are sandwiching.
Yes.
Where is that guy on the right-hand side? I don't see the sigma.
Yes. So the sigma, so intermediate step will be that there will be a, so that is equal to an intermediate step in which I'll write it as sigma over. So when I do this sandwiching, for example, can you see here?
Yes.
If I do this sandwiching of a metric, I'll get an intermediate state which is sigma over k squared d11k e to the power minus ik dot x, something like that. Right? Okay. So I'll get this solution over here. So question is, what value of sigma can give rise to this? First question I can ask. So I can figure out what value of sigma. But consistently, this G mu nu, this G mu nu should also solve an equation of motion. And that equation of motion, in the vacuum case, the equation of motion is R mu nu minus half T mu nu R equal to T mu nu. But now this equation of motion is expectation value of R mu nu minus half expectation value of G mu nu R expectation value of T mu nu. So you have to solve this equation, and that condition that leads to this one. So this guy is, as you have noticed, is called the Schwinger-Dyson equation. So the system also has to satisfy a Schwinger-Dyson equation simultaneously.
So that means I cannot just arbitrarily choose a coherent state.
Yeah.
I have to also tune
Also
that.
satisfy another equation over here. Otherwise, they will all be offshore. Okay, so that's the Schwinger-Dyson equation actually. Turns out it also has to satisfy this one. So there are two conditions simultaneously come. So every equation of motion gets replaced by a Schwinger-Dyson equation. Every state becomes an emergent state in the theory. So anyway, so these details are not important. So this is what you are asking, how this S total looks like. Typically what it looks like, we could not figure out all the coefficient, right? So this is the typical curve. This is the typical piece of the kinetic term, R mu nu, G wedge star G, C wedge G wedge G. And then I add the perturbative series of this particular form. So let's define Q perturbative. I said that I will not take any approximation. Here is what we take all possible linear combinations. So there are 60 such possible curvature terms. There are 40 such flux terms over here. There is also fermion, but I don't put all these. Write a perturbation theory, except that we don't know the coefficient. Write a most generic perturbation theory you can think of, including all possible terms, all possible derivative, all possible powers and all, exhaustively. And then the claim is that the actual action that enters will be these perturbation theory, and then there is an instanton sector given by some kind of this perturbation theory, and then non-local. So there will be, it's a sum over all S equal to 0, which is, will make it to be 1. So S equal to 0 will be the usual perturbation theory we see, and then you have to add back the first instanton sector. Otherwise, the series will remain, series will become asymptotic. So one instanton sector S equal to 1, that will be over here. Then 2 instanton, 3 instanton, up to infinite instanton sector we have to do it. And similarly, there will also be other non-local interactions. So this is a kind of S total which enters in our
As far as number of derivatives are concerned, how far do you go? You need to go.
We don't know.
It sounds hopeless then, doesn't it?
Well, for very large S, it's suppressed very heavily. You can see for very large S, it's suppressed very heavily. So we don't have to go too far beyond, because S equal to say 20 or 30, it's exponentially very heavily suppressed. So we don't have to go too much. In fact,
What was the S again?
S is just integer. He captures the instanton number of the theory. How many instanton we are taking into account? We can take 1, 2, 3, 4, and the number of instanton. Okay, so this is the kind of proposal we made. We don't have to go too far away. And yeah, so anyway, this is how the equation of motion looks like, the Schwinger-Dyson equation. Not gonna solve it. So let me give you an example how all this thing works. Let's take an S total, which is very simple, a lambda phi 4 theory over here. So rest of the time, since I started a little late, I can take. So let's take a simple example how this works. Let's take a lambda phi 4 theory over here. And D I defined in this particular way, sigma phi. That's the way I define the D, which I was telling you about. Okay. Now I want to calculate this one, expectation value of phi, which is G00. Okay. I want to show that this can come out from this analysis this particular way. Okay. So I plug this in. I plug this in the path integral. And this is how you see the vacuum has shifted because of the DD action. And this is how the perturbation theory will look like. Okay, so I expand this. So I'm plugging this in the path integral. So it's all a path integral calculation. You do e to the power of minus s over here. And then you have lambda phi 4 theory. And you put DD dagger in front of it over here. And then you put the expectation value of phi. So this is how the formula looks like. DD dagger goes up to shift the theory in this particular way. And this is the expansion of the perturbation theory. And this is the field I have added, expectation value. So this is the expectation value of the phi. So to show it again, over here, bear with me. So this is, I'm doing expectation value of phi. And that will be path integral e to the power of minus s of phi, d dagger t and phi. This d dagger can go up and it will shift the vacuum over here. And lambda phi 4 theory is here, S kinetic plus S interaction, which is lambda phi 4. I can Taylor expand that guy and I get that. So this is how it looks like. This is how the path integral looks like. Now let's go to the nth order. At nth order, I have this term. At the nth order, you see this goes as g to the power of n factorial 4 pi n volume to the power of n, and this field to the power of 4 pi n. So this is how it looks like at nth order. Same calculation, we can sit down and do it. Now, there is some rules, there is some various rules over here, but you can see from here that if I expand it over here, then you see the most dominant term will grow as 4n factorial. You can see if I binomial expand this, the most dominant term in which all the momentums are different, k1, k2, k3, that will go as binomial 4n factorial. So you see that this term actually grows as 4n factorial divided by n factorial. So the growth of that particular term is 4n factorial divided by n factorial. So you see these terms are actually growing fast. So that means the perturbation theory cannot make sense over here, because if the theory grows as, you can see that if the perturbation theory, imagine I have a perturbation theory n lambda n, and if the perturbation theory is growing as n factorial, this would become bad if this is exactly equal to 1. If this is 1, then we are, because we expect this to be smaller than 1, then only perturbation theory makes sense. Lambda is much, much smaller than 1 times n factorial. If this remains smaller than 1 for all n, we are safe. But if it is become equal to or greater than or equal to 1, we have a problem. So when this is equal to 1, there is a problem. So if we take the log on both the sides, first term will be n log lambda plus n log n minus n equal to 0. Remove n from both the sides, then you find that n is equal to 1 minus log n is equal to 1 minus log lambda. So n is equal to 1 over lambda. So you see, if lambda is 0, then n is infinite. So you need infinite such contribution. But if lambda is slightly bigger than 0, there is a value of n for which the perturbation theory will get screwed up. And you can easily see if I take electro QED, it will turn out to be, since lambda is 1 over 137, n is equal to 137. So at the 137th loop, QED will behave badly, which is what Dyson had observed in his paper, famous paper, the divergence of QED, showing that perturbation theory should not be believed at all. Perturbation theory doesn't make sense. So that's exactly what is happening. So now the perturbation theory doesn't make sense, so they grow in this particular way. So now what I have to do is that this is how the nth term will grow. And this is the factor which comes because of that integration. So this is how the nth factor grows. So now what do I have to do is that this one I have to Borel resum this. Instead of summing, usually I have to Borel resum this. When I Borel resum it, since this is becoming infinity, if I Borel resum it, this will become finite. K is some constant, you don't have to worry about it. So I can Borel resum it. So this will be the expectation value of phi. Expectation of the value of phi at the nth order will go like that times the Fourier factor that comes out from this integration. So I Borel resum it, and lo and behold, I get a finite answer, of course. And that is the expectation value calculation, which shows that sigma has to be related to the Fourier components over here. And this is the result I get from Borel resumming the whole thing. Now you see the whole series in the path integral is summed up completely. The final answer is a wave function renormalization, don't worry about that. And one can see that now to calculate this, you have to find how many poles are there on the Borel axis. And for A to be positive or negative, there is only one pole on the Borel axis. Is that good? That makes sense? And you can also check that if I expand this piece over here, if I take this piece and I expand it over here, which is exactly that piece, you see, I can write it e raised to the power of n over g to the power of something times this. So this is exactly the instant on saddle. These are the fluctuation determinant of all this instant on saddle. So now the claim is that expectation value, I'll claim that this is equal to this because it solves the Schwinger-Dyson equation, which I did not show, but that should be equal to this guy over here. So that means lambda to the power of minus 4th term, t to the power of minus 8th third should be equal to this kind of quantity. So from here you can make a claim that this guy maybe is equal to that guy, and t should come out from this integrating out this particular thing over here. So expectation value of phi, which is actually related to, for example, the expectation value of the metric should. So that means the cosmological constant should come out from the Borel resumming the whole series, and the time dependent should come out. You might see that this distribution may look unnatural. I could have any other, but there is a different way by which you can argue that this is exactly the only distribution allowed from that. So this shows that we can actually determine a closed form expression for the cosmological constant by Borel resumming this series, despite the fact that we don't know much about this one. So we claim that maybe the cosmological constant in this model is a Borel resum quantity of this one. Find over here.
Is this kind of an induced gravity scenario you're discussing? You had a Klein-Gordon, interacting Klein-Gordon theory.
Yes.
In a curve, in some fixed background.
Yes.
And you're computing loops.
Computing here perturbative loop, but summing over all the perturbative loop.
And
So I get
that will give you a gravity action.
that will give us a gravity action.
Isn't that what is in literature called induced gravity?
It's related to that setup.
Related, right?
In fact, some of the authors of this induced gravity wrote us saying that we should cite their work.
So you should probably, yes.
Yeah,
Okay.
so we looked into that and there is some similarity.
So you are claiming that you can get de Sitter gravity in this way.
Yes, that's right.
Is this a new result, or how new is this result?
I haven't seen it anywhere other than Gyadiwali and company. So,
Very good.
and now everything will rely on the fact if this is negative definite, we are screwed, because if this is negative definite, it's not going to work. All our effort will go to vain if this quantity turns out to be negative definite. There are a lot of negative stuff over here. First, we have to find the pole on the Borel plane. We can ask whether this is positive definite or not. It turns out, then we have to run to the mathematician in our building with this problem. Can you show that despite our knowledge of A is not there, since we don't know what A is, because it relies on all these things. Can you show that this integral is always positive definite by taking the principal value? And he gave us a proof, and he became a co-author of that. So the whole paper relied on this thing. So he gave us a nice proof. He found out that, of course, if A is negative, it's clearly positive definite integral. Problem is when A is positive, he showed that even if A is positive, this quantity is always positive definite. So that means cosmological constant at least is positive in our setup. It's a closed form expression. Can this be made small? That's another question you might be asking. So we have not sure. Can be made small or not? It's a work in progress.
How much model dependent is it?
Yeah, or can this be 10 to the power of minus 120 times m Planck square? See, it's proportion to m Planck square. Question is, how much is this? Can this be as small as 10 to the power of minus 120? Say? Well, we have absolutely no idea whether it can be that small. It can give rise to a positive cosmological
How
constant.
much model dependent is this? If you go back to the potential you used. what
Yes,
was
it
the
all depends upon this choice of A, which actually, if you go back and see what A was, A dependent upon all these integral over all these Fourier component from 1 to 4 and all these things. There's a series of Fourier component coming from all the fluxes and all.
Those in turn came from some potential. Was it 5 to the 4 potential?
Here is this 5 to the power of 4.
What if I have 5 square plus 5 to the
Indeed,
4?
it turns out that in all cases, we always get an expression. Yes, thank you for asking. We always get an expression with that kind of, it's always of this form, but A taking some different value. That's the model dependent factor over here. So that's what we were finding. So we find that it can be written in some kind of closed form expression of this.
But this is a dimension 4 and less operators in the Lagrangian.
Yes. To
High
start with,
dimensional operators.
even if you add higher dimension operator,
No problem.
it always somehow takes this particular form.
Okay.
So that is what. So and it always follows that pattern which we showed before, that it is always of this form, that it's really an instant on saddle and over all the fluctuation. Of course, it was all done for a 5-4 theory for this particular case, but in general, it's also like that. But this is our conclusion, that it's definitely positive definite, definitely small, not sure how small it can be made. But again, it was a lambda 5-4 theory, so we don't know what the cosmological. So, so please don't be alarmed. We haven't solved the cosmological constant problem. This is just a scalar field model. The actual analysis will be much harder. However, our analysis suggests that maybe dark energy is a cumulative effect coming from summation of all quantum terms, and it's completely invisible order by order computation. See, we would not have been able to see this if we did not do the Borel resummation. Means at order by order, we'll never see cosmological constant in physics. I believe it's a completely emergent quantity in physics. Unlike anything, as they say, the whole is greater than the sum of its parts. And if we did not know how to do the Borel resummation, we would not have seen that the system condenses down to a single factor over here, which has a positive energy in front of it. At every order, we never see that thing. So the search for cosmological constant as an order by order case, I don't think will ever reveal an answer in physics. I think it's a cumulative effect of everything when summed over Borel resum. Then you can't see that there is something called a positive energy in the system.
But what about the Einstein term, Hilbert-Einstein term? What if I added to the game?
It actually doesn't do anything. It does not create.
Just to normalize the coefficient?
Yeah, just renormalizes the coefficient. It does not give rise to anything.
Plus this stuff, the cosmological constant.
So our analysis might also provide hints on precise reconciliation of GR with quantum mechanics. All non-trivial GR configuration, unlike the Glauber-Sudarshan state, and not like, for example, Einstein was worried about that. Einstein theory was that there is some kind of classical configuration over here, and here is a quantum world. And he could not find some reconciliation over here. But what we think is that this classical physics, I draw it in a symbolic way. The classical quantity in Einstein theory would look like, let's call it, if C is a classical quantity, our analysis is actually looks like Q. All the quantum term conspires to give us a classical configuration. For example, if I have a classical configuration here, over here, in the quantum world, the same classical configuration will be reproduced as an emergent. That means all classical configuration that Einstein was telling us about will be reproduced in the quantum world as an emergent state. So all classical physics will reappear in quantum world like that. And all the equation of motion of, for example, r mu nu minus half g mu nu r equal to T mu nu will simply be replaced by the Schwinger-Dyson equation, which is the same equation but with expectation values.
That includes the higher derivative terms.
Plus this one is with higher derivative terms over T. So now the equation will be expectation value of r mu nu minus half mu nu r. Expectation value T mu nu. And in that sense, de Sitter may actually be just an emergent quantity in the theory. So, and then you see there is still an underlying supersymmetry there in the system. We'll never be able to see this because we are living in a transient state over here. And that state is for this period of time, minus 1 over root lambda less than 0, because we are choosing a flat slicing. In flat slicing, time goes from minus infinity to 0. So 0 is the late time. So in this whole interval of time from minus infinity to 0, de Sitter states exist for a very short transient period of time, after which the system goes back to Minkowski. So there is a Minkowski background over here. These are the coherent state de Sitter. Over here, it exists for this interval of time. After that, it goes back to the Minkowski.
In the real world, the Sitter state seems to be a long-lived state.
The claim is that this is not the case. Apparently, according to Trans-Planckian things, de Sitter should be a transient state in the theory. It should only be over here, beyond which, and that's what now all the people are settling down, Wafa and Robert and all. They wrote a paper saying that there is a Trans-Planckian censorship conjecture in which de Sitter, if it exists in string theory. So their conclusion is that first paper of Wafa says that de Sitter does not exist in string theory. Later on, he modified it after people said that this is not right. He modified the whole paper and he came to final conclusion is that de Sitter string theory would allow de Sitter as long as it is within this bound. We found this bound from a different argument completely, and we did also find this coherent state to exist in this. So we called it the transient de Sitter phase. So if string theory allows de Sitter, this is the best it can allow, in my opinion, unless something else happens.
Inflation scenario, where does it stay? In the inflation.
We don't know yet. That's why I didn't want to answer your question at the beginning. We haven't recovered the inflationary scenario. So now let me show you the last stage. I think I'm done more or less. So here is the change. So this is what we expect in vacuum configuration. Type 2, type 1 heterotic theory will be replaced by M theory and duality system. The de Sitter spacetime in vacuum should be replaced by these states. Fluctuation over de Sitter space will be replaced by another state called Agarwal-Tara state. The Trans-Planckian bound is replaced by this thing. Black hole in de Sitter will be another global motion state. Equation of motions are replaced by Schwinger-Dyson equation. We see that there are no on-shell state in our theory because everything is done using path integral. So all on-shell state will look like off-shell states. Here is an interesting thing. Some of the off-shell states conspire to give rise to on-shell states in our case.
Oh, wait, isn't Schwinger-Dyson equation an on-shell statement?
No, it's an off-shell statement because an expectation value over all the thing. Oh. Schwinger-Dyson equation is a completely off-shell statement. On-shell will be del S by del G mu nu equal to 0. This is on-shell. This is overall path integral. That's the Schwinger-Dyson. So it's a sum over all path that includes even the one that do not solve this equation of motion. So even though this equation may or may not be satisfied, this equation of course is always satisfied. In quantum mechanics, this is the Ehrenfest equation. So off-shell state becomes something like that. The Feynman diagrams are replaced by some new diagram which developed in our paper. The metric is replaced by a path integral. You see, that's the reason why we call it a off-shell case. The conformal time is replaced by this time over here. Internal metric has this form over here. That's where asking whether, so this may or may not be compact. This may or may not be compact, but it at least has to have a compact support. The positive cosmological constant is replaced by a closed form expression of this form, and we expect this to be much smaller than a Planck square. How small it gets, we don't know. The existence of effective field theory boils down to a very simple criteria that the derivative of G string with respect to time has to be a positive power of G string, which implies non-violation of null energy condition. The quantum tunneling in this thing replaced by real and complex instanton. Non-perturbative effect is Borel resummation of this series. Open quantum field theory replaced by now Wilsonian and exact renormalization group, because in our setup this works, of course. Contribution from 0-point energy replaced by no 0-point energy contribution at all. Non-SUSY vacuum configuration was replaced by spontaneously broken supersymmetry. Moduli stabilization replaced by some kind of dynamical moduli stabilization. No Boltzmann brain, because our system survived for this period. There are no Boltzmann brain in the theory. Background fluxes replaced by expression like that. The 7 brain becomes a top knot Glauber-Schudenstein state. The gauge field on the 7 brain became localized expectation of fluxes. The orientiful 7 brain become Atiyah-Hitchin state, and so on and so forth. So there is a dictionary for everything now. Thank you. Yeah.
Great man. This is a very complicated program.
Well,
difficult.
we started that.
But with a nice, very nice.
Thank you very much. Thank you. I don't know, I answered all the questions. You had a very.
It seems you reduce string theory to quantum optic, yeah?
Something along that direction. We want to pay homage to Glauber and Sudarshan, who actually did all of this work in some sense.
And can you comment on what happens with McGill ADN space in separation? Ignoring.
I don't know the answer about that. I don't know the answer to that question right now.
Help with the sitter.
Our initial calculation led to the similar problem of this particular kind, but ask me in a month or so.
I have a question. Can you go back to this no-go theorem? Because there is a solution of the theta embedding by getting given about having a solution 11-dimensional supergravity. I just want to see how this will.
That has a latent singularity.
No, it's smooth, but it's non-compact. But you
non-compact, yes. Newton constant, vanishing Newton constant solution.
Yeah, but your no-go theorem is about something positiveness about that.
With positive, with positive non-zero Newton constant.
Hold on, this is just looking for solutions. We haven't gone to this whether Newton's constant is positive or not.
Oh, this is this is embedded in the statement that the internal space has a compact support.
No, I mean in your original you give this
no-go condition.
No, yeah, you have this summation of multiple parts has to be all positive.
Yes. Okay, good. So this quantity, you see.
Because I don't see where the place of compactness being used.
Yes, so here.
Yeah, okay, that's the equations. The first, there's no assumption of
yes.
the.
So here, D8X is the internal manifold.
Right, that I didn't see. It requires
So
compactness.
internal manifold that supports all integration over internal manifold. So we need this to be compact for this to make sense.
Why? You basically saying the first term will be positive, the second term will be positive.
Third term is positive.
Right, but that is independent whether it's compact or not. If it's a non-compact, it's still positive. As long as it's smooth, right?
If it is non-compact, every term is by definition is blown up over
to infinity, right?
Yeah, infinity.
But
And there is, I mean, we don't have anything to say if it is non-compact completely.
But you would say that it will be ruled out Because it will not be zero.
No, it's not ruled out. It says that, yeah, it will be infinity plus, so it's all positive, whether compact or non-compact, it's always
Then
positive.
all positive. Then you would say this can never be zero, and hence such a solution wouldn't exist. But then there is a such solution.
For non-compact case, I need to check up that thing.
Okay,
I
right.
need to
Because
check.
at least at the moment, I didn't see anywhere.
Here
Non-compact
our,
is,
here
How
is
is it, how is this equation satisfied in non-compact case? Can you tell us?
No, it's precise, the Lagosian, this equation cannot be satisfied, hence such a solution doesn't exist.
Yes.
And the
you say-
non-compact
yeah.
is, then it will not be satisfied.
Yes.
So you would say non-compact solution will not be.
Yeah, okay, that is another issue.
There is a by Galilean.
So how do you then put
Actually,
it together? We don't know.
Then. I
Even
didn't
after
think
that came up with this
would be-
conclusion, it's given Maldasen and Nunes, he came up with that, this is his equation actually, given Maldasen and Nunes condition. Originally it was given, so his claim is not exactly this one, his claim is the following, that any positive energy solution has to satisfy that the trace of the energy momentum tensor along the space-time direction should be greater than the trace of the energy momentum tensor in the internal direction. That is the only condition comes out to be the case. Okay. So in my 2014 paper we wrote, so let me just show you that paper.
But that condition is not a demand, why that?
That leads to the same thing. I
Okay.
can show you that one. So I wrote this paper with this one. 2014, the first one. This stuff over here. This paper, 2014, we saw this problem. We found this, so we wanted to satisfy this equation. T mu mu is greater than 0. This comes out from the fact that if you take R mu nu minus half G mu nu R equal to T mu nu, and R mn minus half G mn R equal to T mn. If you demand that the 4-dimensional curvature is greater than 0, you can just contract this equation and you'll get this condition. To demand 4-dimensional curvature greater than 0, this leads to that condition. The trace of the energy momentum tensor should always be greater than the trace of the energy momentum tensor in the internal space.
Yeah, but that seems to be suggest, so this has nothing to do with compactness anymore, right?
This has absolutely nothing to do with compactness
Yeah,
anymore.
but then we do have a solution.
This doesn't have a solution. So in our 2014 paper, we found that this, if you simply take fluxes, branes, anti-branes, you simply take these kind of fluxes, brain, anti-branes and all, you'll never be able to satisfy this condition.
Yeah, but we have a solution constructed by Gary
Okay, I need to
Gibbons.
check that. I need to, because
Right.
Gibbon himself gave this condition. And then it
Well,
became
he has a
Maldasen and Nunes.
solution of 11-dimensional supergravity without even need anti-brane.
Okay, that I don't know. That thing cannot exist.
That's satisfied. Yeah,
Without
right.
anti-brain, the system is.
I took a picture of the solution. You can have a quick.
Okay, I will. Without anti-brain, the system doesn't even have SUSY breaking condition.
It's an old paper.
Old paper. Gibbons.
I need to check it.
Right. So I mean, this is a solution. I just.
No, the authors, may I see the authors so that I can?
Actually, this is my paper, but we copied. So it's-
Are there any more questions?
Maybe you can forward me that paper.
Okay. Yes. Right.
I'll have a look at it.
I mean, here. Right.
Let's thank Keshav.
I think you are also writing studies about kind of non-compact embedding of. No, if the criticism say, this is non-compact, so we don't consider that. That's I agree with that, but their condition.